So we've been discussing the coherent substrate for a bus-based system. And bus-based system have a scalability problem. We want to build bigger machines. They will scale to a certain extent and basically abruptly stop. You cannot put in more processor and expect better performance. So we have to scale them. We have to have a design that allows larger scales. We're going to look at the coherence substrate again. How do we build a coherent substrate for a scalable, what is called a distributed shared memory machine? But before that, I want to touch upon some thing that is relatively standalone. It's how do you model performance? Okay, this is, you can go to the Kohler and Singh textbook. It's dealt with in chapter 4.1. The crux of the issue is really the user will want to run different code. So you have a machine A, you have a machine B, and I have two pieces of code. And when I scale to a bigger machine, I may use a different version of program A and program B. And how do you summarize all of that information into one number to say this machine is 3 times faster than that machine? Okay. So before we even get there, there is an ongoing discussion about even what mean do you use? How do you average? There is commonly used arithmetic mean, geometric mean, and harmonic mean. Okay? When you have multiple statistics and you want to average them, you have these different options. Which one do you use? Well, mathematically we know that. And this is why a lot of machines would report an arithmetic mean result, because it's simply better. It looks good. Really, there's a lot of different interpretation which one is better. I think for the most part, if the numbers are reasonably similar to each other, doesn't make a huge difference, although there are some consistency issues. So let me give you an example. Here's, let's say, machine 1, machine 2, and I have two programs, program A and program B. Let's just say I measure execution time of these two programs on these machines. The first program runs at perhaps a speed of 1 second. And the other program, let's just call that 2 seconds, right? And on a different machine, I run the same program, but in reverse order. 2 seconds and 1 second. Now, if you just look at this, you'll probably say, oh, machine 2 and machine 1 are about the same. Okay, same speed. But let's think about the notion of speed up. Okay, so 2v1. 2 over 1, the speed up. 2 seconds, 1 second. What's the speed up? Okay, if you still remember speed up, that's the time division. You probably heard about loose term that my program is 10%. I have a 10% speed up. This is usually a sloppy notion. They're really trying to say my speed up, my program is 10% faster. Because the definition of speed up is the inverse of execution time. So 10% speed up really, literally or strictly speaking, means 10 times longer execution time. So when the number is small, I can see why people make that mistake. So we're using speed up in a strict term. So if I execute a program in 2 seconds as opposed to 1, my speed up is 0.5, okay, which is less than 1, so that's slowed down. It's 2x slowed down. And in this case, I have a speed up of 2x. So if I average them out, I get 1.25. So machine 2 is 1.25 times faster than machine 1 in arithmetic mean. You get it? Conversely, machine 1 is also 1.25 times faster than machine 2. Okay, it's the same reason, because it's really just two numbers flipped. Okay, so this is actually interesting. So when you go to work, you get an account, you put money in, someone is managing your money, and they will tell you their return of every year in arithmetic mean, the same problem. So some year they're losing, other years they're winning. Let's say someone lost half of your money, but the other year made up the whole thing, which is the example over here. And they will say, oh, my annual, even though your money didn't change at all, they will say my average annual return is 25%. So you see how ridiculous it is to use arithmetic mean in this case. I think the only way to make sense, to have it consistently, is to have geometric mean. In this particular case, obviously, if I have geometric mean, the average speed up is 1, which is exactly intuitive. Both machines are comparable in performance. Harmonic mean is also useful in a different way. Okay, in this particular case, the harmonic mean would be the average of the inverse of the average of inverse, right? So we would get instead of 0.5, the inverse would be 2 and 2.5. So the average of that would be 1.25, and the inverse of that is 1 over 1.25. So harmonic mean-wise, machine 2 is slower than machine 1 by 1 over 1.25. And conversely, machine 1 is slower than machine 2 by 1 over 1.25. Again, it has this consistency problem, okay? Because this is really just the reverse of the arithmetic mean. But it does have some special use. Let's see, what is that? Use this example. Let's say we have the same weight to these programs. And it's the same thing, right? Machine 2 runs the first program twice as slow, but the second program twice as fast. And now, when we want to use geometric mean, we would say machine 2 is the same speed as machine 1. But suppose I execute the program with this weight, meaning on machine 1, 50% of my time is executing program A, 50% of the time I'm executing program B. That is how I'm using the machine. Now, if that is the case, on machine 2, I would be spending more time, 2.5 seconds or 2.5 unit of time rather than 2. So machine 2 is slower. By how much? By 1 over 1.25 times. This is my speed up. It's 1.25 times slower, or the speed up is 1 over 1.25. Harmonic mean will give you that. So if your program, the weight that you give, properly accounts for the intended importance of the application, then harmonic mean will give you the proper result. So basically, you can imagine my workload being 1 unit of this, 1 unit of that, and so on and so forth, and I want to know that composite application's performance, then you use harmonic mean. So mean is one problem. This has nothing to do even with multiprocessor. This is just uniprocessor. We already have this messy situation. Now let's think about multiprocessor. Okay, so when I have a machine, I would want to show this, and occasionally we will show some of that. Most of our discussion would be how to do things. We're not going to evaluate them. Okay, that's very messy. We're not going to do a whole lot. We're just going to show some plot and assume they're done right. And in fact, it's really an art that is not easy. So let's look at this. This is a very common thing. I have an application, and as I increase the number of processors, I want to measure my speed up, which is the inverse of execution time. Okay, so ideally, I want this line. If I have 1 processor, my speed up is 1. I have 32 processor, my speed up is 32. So linear speed up would follow this line. And very often, you would see something like that. This is a real-world example where the application scales fine, rather linearly at the beginning, and then saturates, and over a certain size, even go backward. Why is that? Okay, think about it. And figure to see if you can find a reason for that. But occasionally we get lucky. This is a different example where we have another application. The color is not very clear, but the straight line is ideal speed up. But the actual result is better than ideal. So it really shouldn't be called ideal speed up, it's linear speed up. So this is a more common case, sublinear, and saturated very quickly. And this is superlinear. Again, think about why. What's possible? Pause the video. Think about it. Well, the answer is this. If you have multiple multiple processors, your cache space also increases. And your workload, if it doesn't change, the increase of your cache space may make the working set fit in the cache, and all of a sudden you have a dramatically smaller cache miss rate, and your program runs faster. So this is sometimes possible. But that brings in an issue. Okay? We've mentioned this before. When I buy a bigger machine, am I really trying to execute the old program? Only run it faster? No, sometimes I want to run a bigger problem. So what we just saw is the so-called AMDA speedup, or problem constraint. It's the same problem. And I want to measure the execution time of running on one processor divided by the execution time on P processor. And that gives me the program constrained speedup, or AMDA speedup. The other way of looking at it is, perhaps the better way of looking at it is, I have some time to burn. I'm willing to wait for 2 hours to get the result. And on a uniprocessor, I get this much work done. And on a multiprocessor with P processors, I get that much work done. And that speed up is time constrained speed up. It's executing for the same time, and let's see how much more problem that I'm solving. Well, this is a little bit of a trouble in reality to actually measure it, even though it is perhaps more meaningful. And the problem is this: how do I measure workload? It's not easy. Sometimes I can compromise and simply measure the number of instructions I executed, assuming each instruction contribute equally. But as we will see, we may have these spin loop code when we talk about synchronization, where I'm waiting for the lock. And so apparently I'm making a lot of progress. I'm committing a lot of instruction, but I'm just in an empty loop doing no real work. So unfortunately, work is not necessarily easy to measure. But if you have an application where you can measure, I am crunching some data. How much data did I crunch? Is it 3 megabytes or 10 terabytes? If you can measure work done, then this is perhaps the more useful measurement, and you might even call that the Gustafson speedup. And that's not the only way. There's even other ways, so-called memory constraint. Okay, you will find out that oftentimes when people buy a very expensive shared memory multiprocessor, they're not really wanting to share, to have a multiprocessor. What they really wanted is a big, gigantic memory that they can fit their database in. Once they have that big memory, they can run a sequential code on that big memory. They just don't want to go to disk that often. But buying a lot of memory, 2 terabytes, 100 terabytes of main memory is very, very expensive. They don't want to have one machine to be able to do that. They might as well throw in all the processors so they can all launch things on the same machine. Some taking a lot of memory, others don't. So you can, do this very weird thing to make sure that you set the problem size to fit memory, and then figure out really what the speed up is. So this is a mess. Okay, it's a messy issue. Sometimes we just show you the speed up, and it's probably just I'm not slow, knowing that that's necessarily oversimplified version, and trying to argue about an inherently complex problem. So that set aside, let's just say we can measure performance, knowing the caveat. Let's see how we build scalable coherence mechanism. So the machine that we're gonna assume is this sort of generic system where we have lots of nodes consisting of processors plus their private caches, and they're gonna interconnect over some fabric to talk to main memory, which can be more than one node. And to make everything work, we will have something called a directory. We'll see what that means. And that would be the whole system. And then we can add more nodes to it, either the memory node for here, or processor plus cache node, or just changing into a bigger network. So this becomes more scalable. If I have more processing power, I can add more communication power to balance it. It's unlike a bus-based system where the bus is very hard to change. Well, logically, this is how we look at things. It's so-called a dance hall organization. Ladies on one side, gentlemen on the other. Processor one type on one side of the communication, memory on the other side. Some machines are physically built that way. You have real nodes that are a memory node, like I explained in the introduction, right? Supercomputing or high-performance microprocessors or high-performance shared memory architectures are extremely expensive. It's a very small market. It's very hard to make money. So you want to leverage commodity components as much as possible. And the commodity component tend to look like this already, perhaps without the directory. So it has some memory, it has some I/O, it has some processor and cache. This is a workstation. You're already selling it. It's a node in your a cloud computing architecture. You have that. It's a rack-mounted machine. And that's what you want to replicate. So then what you want to do is to add whatever is specific to your design and use that. So logically, it may be a dance hall organization, but physically, the directory is at the same point as the cache. This is not an intrinsic requirement. This is simply if you want to leverage COTS component. So what do we want to do? What are the directories? Think about it. What is the directory? What is it that's different here compared to a bus-based shared memory multiprocessor? So SMP, it used to be shared memory multiprocessor. It used to be a bus-based symmetric multiprocessing. Okay, everybody's on the bus. And now we're calling it distributed shared memory system, DSM. Why? The memory is distributed, right? It's here, it's here, it's here. And what's the implication? NUMA, non-uniform memory access, non-uniform access time. If I have a miss from my cache, I will go to the memory. And memory, this is all shared. So maybe the first page goes in there, the next page goes in there, the page after that goes in there, so on and so forth. So I have an address. Based on the address, I know where the page is. If the page maps here, then I go on the network, get to the destination, grab the data, come back. And that may take 2 microseconds or 2 microseconds, yes. But if I miss, the page happens to be local, well, that's easy. It's almost just like a regular memory access in a uniprocessor. So the access time is definitely not uniformly distributed. Okay? So what's the difference? We still want to keep coherence. Remember, what is in coherence? What are the two requirements? Right propagation and right serialization. If you don't remember what those are, pause the video, go back, check your textbook. So right propagation says we have to shoot down, essentially, all the copies eventually at some point, right? How do we do that? In a bus-based machine, how did we do that? Now, what do we have to do? Again, think, pause the video. In a bus-based system, we simply put the address on the bus, and we hope everybody sees it. And that's it. That's the end of the story. Everybody pick up their part of the deal. This is like if you're living in a dorm. You go out, shout in the corridor, hey, who took my whatever, my Nintendo, right? And this doesn't work if you have a very, very large dorm and you have a lot of friends who keep on borrowing your game machine. You can't go and shout and expect everybody to hear it. So what do? You keep a book. You say, X took this from me, Y took that from me, and that's what the directory is. It's a scratch paper. What do you have? You remember who has a copy of what. So for every memory unit, usually it's organized at the size of a cache line. For every cache line, in theory, you have a directory for that cache line recording who has the data. And that's the information. Okay? How do you represent that information? Well, the easiest thing would be full presence bit vector. Okay, so this is my cache line. It has whatever 64 byte. And I'm going to have some metadata next to it, really in the directory. So, and this represents from 0 to n-1 the M processors. If processor I has a copy of it, this bit would be set. So this bit vector at any point would tell me who in the system has the data. And what's the problem? It's not scalable. Suppose I have 10,000, I have a 1024 nodes. Okay, then it's a kilobit. 1 kilobit of full presence bit vector for 64 byte, which is 512 bit. That's 2x extra storage for metadata. Remember, it was sometimes because the expensive memory that we build shared memory machine. Now this is making it much more expensive. All right, so what you can do? Well, if you think about it, this is really what's needed, right? You have your memory, which is organized as a whole bunch of cache lines, 0, 1, to your capacity. You have C cache lines, and then you need a directory. Every cache line has a corresponding directory. So then there is a height of your table, and there is a width of your table, right? And H times W, the height times the width, is the size needed. So you can shrink this, or you can shrink this, or both. There's really no other way around. So that's what you have to do. So how do you reduce height? Well, you recognize the fact that not all memory blocks are present in some cache. In fact, think about how big the cache is. If you have 1 megabyte of cache in each node, and you have, let's say, 1,000 nodes, then at most, you will have 1,000 megabyte or 1 gigabyte of data. In your one node, your memory may be larger than that. So clearly, a lot of the times, the memory block is not present anywhere in the system. You don't need a directory entry for those lines, okay? So it's very easy to keep a subset of the memory lines tracked in the directory. So that's how you reduce height, and it's usually called a directory cache, meaning it's not a full directory. It doesn't have an entry for every single line in the memory. What about width? Can you make the width smaller? Because this is ridiculous, right? 1024-bit. Again, that's sort of recognizing this notion of perhaps you can call it some sort of locality. At any point, a small number of sharer might be sharing the block. Okay, over time, maybe a lot of nodes would eventually use a particular block, but at any particular moment, maybe a small number. So one design says, okay, how about we use pointers or IDs, right? If I use a 10-bit pointer, I can represent one user per 10-bit, and I can have maybe a handful of those, let's say 4. So at any moment, I can remember 4 sharers in a machine with 1024 nodes. So that costs me 40 bits. 40 bits compared to your 512-bit, now that's only 8%. That's a lot better. So, and what is another common use? Well, instead of 1 bit, the bit vector, 1 bit representing one node, it might be representing a group of nodes. All right? If you have a group of nodes being represented by 1 bit, and then when you want to invalidate, and you don't know exactly who inside that group to invalidate, you have to send it over there and then broadcast. So there's trade-off. It's not for free. There are lots of these things. And in fact, some people even come up with something called a scalable directory design. I'm not sure that's a good idea, but that's what they've been, you can think about the worry they had about this. So the idea is this. Instead of putting a bit vector or a fixed number of pointers, we just have 1 pointer in memory per memory block. And that's going to point to only 1 node. And every node, and this is a cache, will have another pointer to point to the next node, and so on and so forth. If you wish, it can be a doubly linked list, or it could be a singly linked list. It's up to you. So then this is scalable. This is just like software, right? Data structure. Linked list, flexible, not like array. Okay, and there's even a name for it, Scalable Coherence Interface, SCI. So this is trading space. Now your space is completely bound. Okay, so you have 1 entry per memory, 1 entry per cache, or 2 entries per cache. It's fixed. It's completely scalable. You add 2,000 nodes, you don't have to change the design. Okay. So this is probably pushing the scalability property to some extreme. So we're not going to worry too much. In fact, there's many different little ideas. Even a couple of years ago, this is probably a 40-year-old problem. Back when SCI was being discussed, I think perhaps before 1980s. So this is a very old problem. But even a couple of years ago, we've been working on it and came up with some observation that hasn't been used, and it can dramatically reduce the amount of storage you need by exploiting totally different properties. So it's something that you can work on. We're not going to worry about it. We're going to make the assumption that that's done. We have the directory, and the storage overhead is going to be fine. We just worry about how to build a correct coherence protocol. Okay? So again, the very first thing that you need to do when you're designing this thing is to make sure it works. Okay? Once it's working, we can start to think about optimization. So what does it mean? Well, you have to follow all the serializations. If you have coherence, now you need to support write serialization because it's cache coherent. And you have to worry about write completion because that's important for the consistency model, right? If you have sequential consistency, the write has to be completed before subsequent reads and write are allowed to go out to make themselves visible to the system. So you need to worry about that when the completion happens. And if you have a really strong consistency model, you may have to support write atomicity. That's something we have to revisit to see how that works. Let's say you think you did all of that, but then the way you do things involves sending nags or whatnot, and then you cause deadlock. Then your system is not correct either. Let's say you solve the deadlock problem by backtracking. What about live log? What about starvation? In general, starvation is not an issue if you don't have live log. Okay, it's just a probability game. It's highly unlikely for one particular node to be starved, but it's possible. So we're just going to ignore that and focus on deadlock mostly. So how is this different from bus-based system? Well, when we have a split transaction bus, we no longer have an atomic bus. So a transaction now is no longer physically atomic. Okay? But at least the state change is still atomic. Oh, someone invalidates us. Let's just change the state. Everybody does that when one transaction is happening. Now that's no longer true. That's no longer atomically performed. We have a directory. If you want to shoot someone down, you have to figure out who has the data and send individual requests over the general purpose network. There's no bus for you to shout. Okay? You have messages. Messages go on the interconnect in various routes. Some arrive early, others arrive late. And they can be overlapped with another attempt. There's all kinds of possibilities, races. Okay? A race is basically two different things, transactions happen with different times. Sometimes one happens earlier, sometimes the other happens earlier, and you have to worry about this. And the network, if it gives you out of order message delivery, not necessarily as intentionally to optimize for something, just because we send a packet this route, we send another packet another route, and some can encounter congestion, and you may have what you think is a bizarre situation. And we'll see that. We'll see an example exactly. So suppose you send an upgrade request. You tell the directory, I have the cache line in shared state, but I want write permission, so we call that an upgrade. Okay, an S wanting to go to M. So that's an upgrade request. I send it to the directory. No, the directory remembers who has the line. The directory says, currently the line is not owned by anybody. Okay? It's not in any cache. Unowned. You say, that's impossible. I tell you I want to upgrade, so I have a copy. Well, it's possible that your system is designed such that after you send the upgrade request to do this, the cache controller got another piece of data and decided to evict the initial data. And not only does it want to evict it, it also wants to tell the directory, I don't have this piece of data anymore, I evicted it. And so this message arrived to the directory first. So the directory says, oh, you're the only one who holds it. Turns out everybody else dropped their data too. So now this is unknown. And then boom, your upgrade request arrives later. Okay? Is it bizarre? Is it unintuitive? Yeah, sure. But it happens. And you better not reboot your machine because some bizarre quote situation happens. So the takeaway message is, in general, you need to consider all possibilities. You cannot just say, well, this doesn't make sense. You have to think about whether it's possible. Okay, you cannot just assume let's handle the intuitive situation. So how to send these messages? And it turns out that actually matters, and people even give them names. Okay, and we'll see how they matter slightly later. So here it's all going through the same kind of figure. We have home. Home is the node that has a particular cache line. So I have a, if we go back here, we have this machine, right? So, or maybe here. Let's get rid of all of that. So here, remember, the memory is logically shared by everybody. Okay, so this is one big piece of memory. So every cache line has a fixed location. Maybe address X is in memory here. Then this node is the home node of address X, because this is the node who handles to coordinate all the coherence transactions related to X. So that's what H stands for. And we have two nodes, left and right. The left sends the request to the home to say, I want X. Home tell you, too bad. I don't have it. This other guy, R, has it. And then L then send a request to R to say, well, then I need address X. R provides the response. And also remember, when someone reads from an updated, modified data, we have to update home. So this is what happens. This is strict request reply. You send a request, you always get a reply. Okay? Well, sometimes you say, but that's silly. Let's say if L node is here, R node is here, okay, and there are more nodes, and the home node of a particular cache line is here. L goes through the interconnect to get to home, and home, well, actually this would be a bad example. I have to make it more contrived. L would be here. M, let's say it's here. No, actually, let's put it this way. Yeah, this is fine. Home is here and R is there. Okay, so go to home, get the result back, go a much longer route to R to get the result back. Okay, so obviously, because of the triangular relationship, going from H to R is going to be no worse than sending back to L in order to go back to R. So that happens. Sometimes we do this. You want the data, oh, I don't have it, but I'll send the intervention request on your behalf, which the node would obviously reply, okay, updating memory, and I can forward you the data. Or we can do this in parallel, so you get the data slightly earlier in most likely cases. So you have different messaging styles. Okay, this will change the performance. Obviously, this looks like would be the fastest, but it has implications. It has low requirement to avoid deadlocks. We'll see how that works just a minute. But these are all trade-offs, and people have to consider them. Okay, so for correctness concern, we have to worry about deadlock. And this is the deadlock that we're going to deal with first. So in general, deadlock is a dependence loop. Some operation depends on other operations, which circularly depends back on the same operation, and then you have a loop. Okay, let me give you a very contrived example, and to introduce this concept of deadlock. Let's say I have a bus-based system. Okay, P1 issues a read request, R1, first read request. This would require P2 to write back. Okay, and P2 also has a read request, which is R2. And when R2 issues, it needs to make P1 write back. And so this is the sequence. I get the bus. At one cycle, both of them generates the same request. Each one generates an individual request. One of them gets to the bus. Okay, fine. And this is a split transaction bus. So the minute I get this demand of write back, I put it in the outgoing queue to say, okay, that request will go out after everything before it has finished. But conversely, read to requires the previous owner to write back as well. So now, I guess this should be 1, just to make them different. So now I have the situation of R1, okay, is depending on WB, R1 is follows WB2. Okay, you have to write back before I can finish. But WB2, because of this, again, contrived example, because of my FIFO outgoing queue, has to be queued after R2. If R2 doesn't finish, I cannot allow W2 to go on. But R2 needs write back 1 to happen before it can happen, which is queued behind R1. There you go, forming a circular dependency, and I have a deadlock. Now, before you say that this will never happen, something like that can actually happen, and that is called a fetch deadlock. Today, some people call it protocol deadlock. I grew up reading the textbook. When I go to grad school, the textbook that we're using, it names it the fetch deadlock, so that's the name I'm using. Again, I don't know what committee decides these names, so I'm going to call it fetch deadlock. We will see why. Protocol deadlock is a pretty good name because this is the coherence protocol's deadlock. We will see later on when we have an interconnect, the interconnect itself can have deadlock. It's a big headache for interconnect designers. This has nothing to do with this. This is assuming the network doesn't have any possibility of deadlocking. It is the coherence protocol that creates the deadlock. But we're going to call it fetch deadlock anyways. The idea is similar: resource usage dependence. This is what I was explaining, the analogy that I was making in the other video, where I have 2 apples and you have 2 pears and we want to exchange. But the rule is I can only give you a piece of fruit in an empty hand, into an empty hand. If I have 1 apple, you have 1 pear, no problem. We can finish this transaction. But if I have 2 apples in my 2 hands, or if you have a religious belief in the 1,000-hand Buddha, whatever creature, and you have 1,000 apples, you still have a deadlock situation. But this is actually pretty close to what's to the reality. It's if you have enough buffer or enough hand, you're unlikely to have this situation of a fetch the apple deadlock. So how does that work? Well, I have 2 nodes. Okay, the 2 nodes are sending. Again, this is a contrived example. In reality, you really have just 2 nodes pinging back and forth between each other. It's usually a multi-party situation, but 2 nodes will explain the situation. Okay, suppose I have a whole bunch of incoming requests. Okay, P2 is just crazy, sending a whole bunch of incoming requests to P1, and it filled the queue. Meanwhile, P1 is doing exactly the same thing. It's sending a whole bunch of requests into P2. And even though some of the requests may be buffered temporarily along the route, eventually, if I keep on sending enough of them, this would happen. P2 will want to send me a reply. Okay, I got your request, here's the reply. But I can no longer send any reply because the channel is completely jammed. I'm waiting for you to remove a packet from the channel before I can send a new reply. But you cannot remove anything until you can send through the packet that is already in your outgoing queue. But you cannot send through anything in your outgoing queue unless the receiver syncs in some of the requests at its doorstep. And this is exactly the let's exchange Apple kind of dilemma. Okay? And that's called a fetch deadlock. Right? So how do you solve the problem? How would you solve the problem? Pause the video, think about it. So deadlock prevention in general, deadlock situation is in general handled in a couple of ways. You prevent it, you make sure it never happens, or you allow it to happen and subsequently do something to dig you out of the hole, so to speak. So how do you prevent the cycle, I should say, from forming? Well, it's actually not too difficult. Let's say I have a network only for replies. Right now I have two generic pipelines. This is, west going, this is east going, whatever. But any type of packet can go. But imagine a separate lane. This lane is only for replies. Okay? The channel. Only for replies. You cannot send a request in that channel. If you do that, then anything in the reply channel will not be blocked. They will eventually be sourced, be taken away by the receiver. It's a reply. Okay? You can always take a reply. You send some requests and you're waiting for those reply, and when a reply comes, they don't generate any new request. So they're not dependent on anything. You can just yank them from the pipeline. And if you do that, then the situation will never deadlock, because I can always send a reply. Because I can send replies, my outgoing, at least the buffer dedicated to the reply channel, will eventually drain. That will allow me to take requests and service them, therefore draining anything that is clogged in the request channel. So this works if you have another network dedicated just for a reply. Okay? It doesn't have to be a real network. If you made it in a way that it uses the same physical channel, but it's a virtual network, we'll explain virtual network in more detail, but right now just think about that the different virtual network time multiplex, for instance, share the same underlying physical channels. And if you can do that, you can have a system that will not have a fetch deadlock. Okay? And this is why, if we go back to the style that we were discussing over here, we care about having these different styles. In this strict reply and request system, there are only two types. So if you have a reply and a request channel, you're done. If you have more, if your chain can be this long, then it's a little bit different. And you could get away with fewer channels, but in general, you might need as many channels as the number of different types of messages. Okay, so that's why sometimes a strict request-reply protocol is good. But of course, if you have dedicated resources, it's always underutilized or less utilized than if you have shared resource. Okay, so that's always a trade-off. And so what is another solution? Well, my analogy of the 1,000-hand Buddha, whatever they're called, I'm sorry, is actually not irrelevant. So if you have sufficient buffering, meaning you have a lot of hand, and then you can practically solve the problem of exchanging apples. Suppose you say, I make sure nobody will ever have 2,000 apples to exchange. The most you will have is 1,999. Then having 2,000 hands would help. you would always have an empty hand to receive a pair, and therefore creating another empty hand on the other side so you can push an apple and you can exchange. Okay? So suppose I have a 512 node machine. Okay? So what's the problem with this? Is anytime you have a worst case scenario, it's an overkill, it's bad, right? Suppose we limit the outgoing request to 2. Then for sure we know no way we're gonna have 10, 25 requests queued up on one node and somehow overwhelming that machine and making him not able to reply. So long as it can sync in 1024 plus 1, it can always absorb any amount of temporary traffic and not clog the system. But this is terrible, it's inefficient. If I have a million node machine, even allowing just one outstanding request would require a worst case a million entry buffer. It's obviously ridiculous, which is why you can solve the deadlock problem by allowing it to happen and then take care of it later. Okay? And that's using NAC. When your input buffer is full, you NAC it. You can sort of assume or think about it as if you're deleting it. So you got a message, you take it in, but you throw it away because you don't have a buffer. And you NAC that packet. If you don't NAC the packet, the sender may wait for a long time. So it sort of deletes an unwanted message. Okay, so we don't have to limit. Well, then, of course, you would say, well, how do I send NAC? If I can send NAC, I could send a reply. But sending a NAC can be easy. It's easier. You may have a dedicated link that is somehow cheaper to build, and it only allows you to send NAC. Okay. And so this gets complicated in one particular design. In Dash, Stanford machine, for example, they have 2 virtual networks. They don't use a strict reply and request protocol, so sometimes they may have a deadlock situation. And when they do that, when the incoming buffer and outgoing buffer are getting full, they say, we're getting into a deadlock situation. They start to NAC the request and revert back to a strict request and reply type of protocol. So the reply network will always sync these NAC and any replies. And so that's one way they dealt with fetch deadlock. So if you have NAC, does that solve the problem? No, right? If the systems keep on sending NAC to each other and they keep on trying to send the request again and being NAC'd, and that can fall into a live lock situation. Of course, it's possible. But depending on the design, usually it's not easy if you back off in some way, because it's unlikely that this would get into the exact same situation. So some node might be making forward progress. Okay, and if some nodes are making forward progress, it's no longer a live log. But can you have starvation that some nodes keep on being nagged? It's possible, and sometimes there are solutions. Sometimes there are guarantees in the system. Okay, for instance, in the Origin 2000, the request will keep a timestamp or keep a counter on how many times it has been nagged. And when it's been nagged so often, it will gain priority, so it will reduce the odds of being causing starvation.